Yeah, good evening, everyone. I welcome you all to the Student Research Seminar Series 2021. I'm Marky, I'm one of the hosts for the evening. So this is a monthly event showcasing the research done by IISc on a public platform. So today we'll be having two very interesting talks lined up for you by students from the EC and from the W departments. So before we begin, for the records, I would like to know how many of you are an IEEE member. So may I please request all the IEEE members present here to raise the hand so that we can get a count. Okay, thank you. You may unraise yourself. Okay, so without further ado, first talk of the evening called Distributed Controlled Correlation Testing by K.R.Sahasranand. K.R.Sahasranand studied BTech in Computer Science and Engineering from Ahmedabad University, Kerala in 2009, and worked as a scientist engineer at Indian Space Research Organization, Bangalore, 2010 to 2011. He completed his master's in electrical communication engineering from Institute of Science, Bangalore in 2015, where he is currently a PhD student. His research interests include detection and estimation, information theory, and signal processing. Welcome, Sahasranand, and the floor is all yours.
Can you hear me?
Yes, we can hear you.
Yeah, thank you, Vaki, for the introduction and also for this invitation. And I would also like to thank the organizers for giving me this opportunity to present my work here. So let me share the screen. Yeah, so can I start?
Yes, sure.
Yeah, thank you. Hello, everyone. Thanks for joining this session today. So we'll be discussing distributed correlation testing. This is joint work with my advisor, Professor Himanshu Tyagi, in the C department at the Indian Institute of Science. So we'll be mostly focusing on the theoretical aspects of this distributed high correlation testing problem. But one can as well think of many practical settings in which this arises as a canonical problem, such as Internet of Things, or say consider a wireless sensor network, where these sensor nodes, there are a few sensor nodes which are deployed in an environment, and they are supposed to collect some data about the environment. Maybe they are collecting their temperature sensors, or maybe they are moisture sensors. So these sensor nodes are deployed to collect data from an environment. So since they are deployed in the same environment, and they are close to each other and they are monitoring the same phenomenon, we expect that the numbers that they report have got something to do with each other. But sometimes these nodes can be faulty, and they could report observations which are inconsistent with the rest of the. So a node can turn faulty, and it can produce erroneous measurements which are inconsistent with observations of the other nodes. And this could be due to various reasons, like harsh environmental conditions.
Uh,
Uh,
so this could
so
be
this
due to
could be due
various
to various
reasons,
reasons,
and
and
fault
fault
diagnosis also
diagnosis also
involves
involved
probing
probing
these
these
nodes
nodes
and
and
figuring out
figuring out
if there
if
is
there
a
is a
problem or
problem
not.
or not.
So
So
the
the
problem that
problem
we
that
are
we are
interested in
interested in
here
here
is
is
that
that
to
to
test
test
if the
the
observations
observations
of
of
a
a
node
node
is
is
uncorrelated
uncorrelated
with
with
that
that
of
of
a
a
neighboring
neighboring
node,
node,
because
because
in
in
that
that
case
case
there
there
is
is
a
a
possible
possible
malfunction
malfunction
in
in
one
one
of
of
these
these
nodes.
nodes.
So we want to detect the presence or absence of correlation between the observations of two neighboring nodes in a communication efficient manner. So why
You can.
communication efficient? Because these nodes are typically low cost, low power devices. So they can't communicate so much. They can always collect data. They can keep observing the environment and collecting data, but communication is costly. So we would like to detect the presence or absence of correlation between the observations of two nearby nodes. So basically test between data. So this is the real world setting, but how do we model this mathematically? The mathematical framework that allows us to do that is that of a binary hypothesis testing framework. So a simple, consider this simple binary hypothesis testing problem. where we observe independent and identically distributed samples. Your samples comprise these the pairs of random variables xi, yi, x1, y1 through xn, yn. We would like to distinguish between the two hypotheses h0 and h1, where under h0 the xi, yi have a joint distribution p0, and under h1 xi, yi have a joint distribution p1. We do not know which of them is occurring. So we design a test which takes as input all these observations xi, x1, y1 through xn, yn, and it declares either 0 or 1 to stand for p0 or p1 or h0 or h1, such that the false alarm probability is less than delta and misdetection probability is less than epsilon. So these are some guarantees that we would want out of such a test. So far as standard setting, where this has been studied a lot, but the twist in our problem is that we are in the resource constraint setting, meaning we are in the distributed setting where the samples are not available at the same location. The two nodes are observing data, and say we call one of the nodes party 1 or p1, and he's observing x1 through xn, and party 2 p2 is observing y1 through yn. So if they were both available at the same location, we could have applied a standard test like we saw in the previous slide. But then these are in two different locations. So somehow party 1 has to communicate a few bits, say L bits, and using these L bits and his observations, P2 has to declare either H0 or H1. So this is the distributed hypothesis testing setting. We want to minimize the communication while retaining the probability of error guarantees, meaning the false alarm probability less than or equal to delta and misdetection probability being less than or equal to epsilon, which we obtained in the standard setting, that has to be maintained. So what is the minimum communication required to achieve this? That is the question that we are interested in. So first we look at the simple case where these parties P1 and P2 are observing x1, xis and yis, and look at the case where xis and yis are bits. So these are uniformly random bits. So at each party's end, they look at only their observations, they look like uniform random bits. And we would like to test if their joint distribution of these bits is BSS row or BSS 0. So BSS stands for a binary symmetric source. So as a joint source xi yi is a BSS binary symmetric source with parameter rho. If you think of these zeros and ones as minus ones and plus ones instead, so if the expectation of xy in that case is equal to rho, then we say that the source is a binary symmetric source with parameter rho. So we want to test if the source is a binary symmetric source with parameter rho, or does it have parameter 0. What I mean by parameter 0 here is that the two observations are independent. If x and y are independent, then their correlation will be 0. So their joint distribution is a product distribution. So we want to test if they have a joint distribution BSS rho or if they have a product distribution. So they have these observations at either ends. Now party 1 has to send something to party P2, right? So a simple scheme would be to just pick up a subset of these samples and send it to P2. Now P2 has all these samples, his observations as well as the subset that he received, and using this he can just apply a standard test which involves using samples at the same location. So this is one simple scheme. But how many bits should we send? Why I'm asking this question is because we want to ensure that the probability of misdetection and false alarm are less than epsilon and delta respectively. So what is the number of bits we should send to ensure this? So using the finite sample version of Stein's lemma, which is a standard result, we can show that the number of samples that party 1 has to share is given by this expression here, 1 by 1 minus h of 1 minus rho over 2 log 1 over epsilon. But the question that we are asking here is, can we test by communicating fewer bits? So the simple scheme is fine, we all can understand that. But can we test by communicating fewer bits? What I am asking here is that maybe if we allow the sensor nodes, the parties to collect many more samples locally, because that doesn't involve much cost. Somehow collect more samples locally and condense all of this information into fewer bits, and then communicate only that, and then achieve the same probability of error guarantees. Can we do that? That is the question we are asking here. So the answer is that we can. So we show that the minimum communication with which we can achieve this is given by this expression here, green colored, 1 by rho square log 1 over epsilon plus this extra term. So you can see that the coefficients here are different, and the second term, the green term is smaller than the blue term above, because the denominator rho square is greater than the denominator there, 1 minus h of 1 minus rho over 2. So this the communication here is smaller than that of the simple scheme. So what is the scheme that achieves this smaller communication? Let's look at that scheme. So the proposed scheme is this. You reparameterize the observations zeros and ones into plus ones and minus ones, and think of the observations as n-dimensional vectors. So there are n observations at each end. So think of x as an n-dimensional vector with entries plus ones and minus ones. Y is also an n-dimensional vector with entries plus ones and minus one. So we have represented their observations as points in this n-dimensional space. Now, in addition to these observations, these two parties have also access to these 2 to the L points, which are also in the n-dimensional space with plus and minus 1 entries. And there are 2 to the L of them. So these are called, this is called shared randomness. So they share these random, they know these random points, they share this information. So in order for one party to specify any one particular point, black point, he just has to communicate L bits, because there are only 2 to the L of these black points. So now what is our scheme? Party 1 checks if the observation, if his observation vector is close enough to the first random vector u1, meaning he checks if the distance is smaller than a particular threshold. So he says it is too far. Then he looks at the second point. If that is close, no, that is also too far. Looks at the third point. Yeah, looks like this point is okay. It passes this test. So now he sends, so he has to tell the other party, okay, this 3 is close to my observations. So how does he do that? He just has to communicate L bits corresponding to the number 3. So he sends that. Now party 2 knows this point 3, and he checks if his observation is close to that point or not. If it is close enough, he'll declare that okay, x and y are jointly distributed. If he thinks that 3 is very far from y, then he says that yeah, x and y have got nothing to do with each other, they are independent. So this is the scheme. So formally the scheme looks like this. Party 1 sends b to the L, meaning it's a sequence of L bits, which is a function of his observation vector xn and the shared randomness u. Party 2 takes as input his observations yn, the received bits bl, and the shared randomness, and declares either 0 or 1. This is the general form of a test. Even the first simple scheme is of this form, right? Because there was no shared randomness, but this f just picked out a few samples from xn, and that is what we sent, party 1 sent. So this is the general form of any test. So such a test is called an L delta epsilon test. If the amount of communication, the number of bits that we send is L, and the guarantees, false alarm misdetection probability guarantees are upper bounded by delta and epsilon. Such a test is called an L delta epsilon test. So we seek to characterize this quantity where C delta epsilon, which is the minimum L for which there is an L delta epsilon test for some n. Some n means the parties are allowed to collect as many samples as they want, but we want to characterize the minimum communication incurred to apply this test. So using the proposed scheme, the scheme that we just now saw, we can establish that the communication required is 1 by rho square log 1 over epsilon plus this extra term. So this captures the communication incurred in terms of epsilon. So we can also do similar calculations, which I am not doing here, but and show that the dependence on delta is it looks like this expression here. This also slightly this is similar to the previous one where we had 1 by rho square. Here we have 1 by rho square minus 1. So this is what the scheme gives. Now, is that the best we can do? So towards that, we would like to establish a lower bound. So we would like to say that for any L delta epsilon test, you have to communicate so and such quantity. If that such and such quantity happens to match whatever we achieved here, then our scheme is optimal and we have obtained a complete characterization of the communication. So let's look at that lower bound. So now for any LDL epsilon test, you can communicate L bits. So these L bits can take 2 to the L values. Let me call those values as 1 through capital L. So I also additionally defined a set AI, which is the collection of all those observations for which party 1 sends the index I, and BI as the collection of all those observations yn for which party 2 upon receiving index I declares 0. So basically AI cross BI is that subset of xn cross yn for which party 1 sends the index I and party 2 receives this index I and declares h0. This is that subset where we declare h0. So for any L delta epsilon test under h0, when the true distribution is h0, the probability of declaring h0, so AI cross BI is the set where we declare h0, right? Or rather union over all i's AI cross BI is the set where we declare h0. So that probability should be greater than or equal to 1 minus delta to meet the criterion on the false alarm. So this equation has to hold true for any L delta epsilon test. Now we can apply a Cauchy-Schwarz inequality to this Px and Yn AI cross Bi to obtain the second step. And from there we apply a Jensen's inequality because the square root is a concave function and we get here. And in this step, you can notice that this Px and AI times Py and Bi is nothing but the probability of the set where we declare h0 under the product distribution, meaning under h1. So under h1, the probability of declaring h0 has to be less than epsilon for any L delta epsilon test. So this has to be less than or equal to epsilon. So hence we get this inequality. So recall that this capital L is nothing but 2 to this little l. So little l has to be greater than or equal to this quantity here. So I have written it in this form because we are interested in the dependence on epsilon. Now recall the upper bound, which said the communication is less than or equal to 1 by rho square times log 1 or epsilon. But our lower bound says 1 log 1 or epsilon. So we can we have to check what happened there, right? Because our lower bound is saying 1, but here we have 1 by rho square, and you may have noticed that rho is smaller than 1. So 1 by rho square is much larger than 1. So somehow there is a mismatch here. So let's examine what happened. We use a Cauchy-Schwarz inequality where we upper bounded this probability of joint distribution being less than square root of px times a py times p. So we could have used the Holder's inequality, which gives this upper bound instead of Cauchy-Schwarz. With exponents, instead of half, you have 1 by p prime and 1 by p, where 1 by p prime plus 1 by p is equal to 1. So we use this inequality instead of Cauchy-Schwarz, but with a strengthening, which is that we replace this 1 by p with 1 by q, where q is less than or equal to p. So this is possible if this source is a PQ hypercontractive source. What I mean by that is a source xy is PQ hypercontractive if for every real valued functions f and g, you can write expectation fg is less than or equal to p prime norm of f times q norm of g of y. So we use this f and g to be indicator functions of a and b to obtain this expression here. So using this bound and doing calculations like before, we can show that the communication is greater than or equal to p by q log 1 or epsilon. So here we had 1 log 1 or epsilon. Now we have p by q, and p by q is greater than or equal to 1. So it's possibly some improvement. But still the upper bound said 1 by rho square. So now we have p by q, some other parameters. So how do we get 1 by rho square from this p by q? Luckily for our binary symmetric source, xy is pq hypercontractive if q minus 1 by p minus 1 is greater than or equal to rho square. Rather, the region where xy is pq hypercontractive is characterized by rho square itself. So we can reparameterize p and q in terms of rho square and optimize the lower bound, and we get exactly what we wanted, which is 1 by rho square log 1 over epsilon. So this matches the upper bound. So it is dependence on epsilon. Similarly, we can do calculations on the to get the dependence on delta also, where we use the concept called reverse hypercontractivity, where the inequality is in the other direction, but the characterization is still in terms of rho square. So this kind of settles this problem, and we can use the same scheme to obtain results for certain extensions, like say composite independence testing, where we would like to resolve between again BSS row and independent case. But earlier we assumed that row is known, but here we say that row is unknown, but it is known that rho square is greater than or equal to tau square. So this is somewhat a generalization of the previous case. And previously we got 1 by rho square. Here we'll get the communication as 1 by tau square. This again can be achieved using the same scheme with slight modifications. Another extension is that we want to test between two correlations, say either xi by I are distributed as BSS row 0 or row 1, where both of these are known. Now how do we test between these? What is the communication needed for that? So again, we can show that the communication is of the order 1 by rho 0 minus rho 1 whole square. So if you substitute rho 1 equal to 0, you get back the original result what we had. Now we were talking about observing bits and communicating bits and all that, but all this holds also for a Gaussian symmetric source where x and y are jointly Gaussian. They are zero mean unit variance Gaussians, and they have a correlation of rho. Even in that case, all of these hold true. All the upper bound, the lower bound, the characterization of the PQ hypercontractivity region, everything holds true for Gaussian distributions also. Also recall that we said we allow the parties to collect as many samples as they want. We only want to minimize the communication, right? So if they are allowed to collect as many samples as they want, we can as well do the following. Take subsets of those samples and replace them with their sample averages. Now you can apply central limit theorem and claim that all these random variables are more or less like Gaussian. So we only need to focus our attention to Gaussian sources. Whatever we said for binary sources hold true for Gaussian sources, but now we are saying that for any distribution that you start with, you can anyway convert it into a Gaussian distribution and then solve the problem for the Gaussian distribution. So we just need to focus our attention on Gaussian distributions. And so far, whatever we have derived also hold true for Gaussian distribution. So now we have looked at one-dimensional cases. Now let us go to higher dimensions. Again, these two parties are observing xi's and yi's, but now xi is not a scalar anymore. Xi is a vector. It's a vector with d entries, and each of them is a Gaussian random variable. It's an independent Gaussian random variable. And yi is still observing a scalar, but it is not observing bits. It is observing a Gaussian random variable, which is also a sequence of independent random variables. Now, if you notice, the correlation is not a number anymore. The correlation is a vector. So the correlation vector comprises these entries, where the first entry is the correlation of the scalar y with the first entry of x, then correlation of y with second entry of x, and so on up to d entries of x. So the correlation is also a d-dimensional vector. Now the question we are asking here is whether this correlation vector has energy greater than tau square or is it 0. So whether the squared norm of this vector rho is greater than tau square or is it equal to 0. We would like to characterize the minimum communication in terms of t and tau square. This is the goal here. So our approach is to reduce this d-dimensional problem to the one-dimensional problem. So how do we do that? We'll come to that. We recall that for the one-dimensional problem, say if we want to test if y is correlated with one of the coordinates with some correlation, say tau square, then we know how to solve it using the scalar results that we derived previously. But here we are specifying the problem in terms of the overall energy of the vector, not individual energies, right? So we have this condition, norm rho square greater than tau square. So how do we reduce this d-dimensional problem to the one-dimensional problem? So imagine the following scenario. Suppose the energy tau square is equally distributed among all the coordinates 1 to d. So each of them have energy roughly tau square over d. So then we can just pick up one of the coordinates, say the first coordinate, and check if it has correlation greater than tau square over d with y. If it were indeed 0 to begin with, then the first coordinate will also have 0 correlation with y. So now you can just run the one-dimensional test and then use the same result for this d-dimensional problem, provided the energy is equally distributed. But that may not be the case. So here I have plotted coordinate in the x-axis and correlation in the y-axis for two correlation vectors. Both have energy 0.352. But in the top case, the energy is more or less equally distributed. So we can apply that strategy, that where you pick up one of the first coordinate and test if x, the first coordinate of x and y have a correlation which is greater than tau square over d, or is it zero. The one dimensional test works. But it could also be that the correlation vector looks like the figure in the bottom, where it is some coordinates do not have any like zero correlation with y, some have very low correlation, some have very high correlation. So you do not know which coordinates have what correlation. So you can't pick up the first coordinate and do the test that we just described. That doesn't work. So what comes to our rescue here is a random rotation. What we do is we apply a random rotation to the observations x, which is tantamount to applying a random rotation to the correlation vector. So what does this random rotation do? This random rotation is basically a matrix with entries plus ones, and random entries plus ones and minus ones, and normalized to make it orthonormal, and you multiply the observations with that matrix. So what happens to the correlation is that this bottom figure turns into something like this. Here you can notice that the correlation is more or less spread uniformly. Rather, none of the coordinates have too low a correlation with y. So you can pick up one of the coordinates and then just run the test on that coordinate with y, the one dimensional test. So here I plotted the absolute value of correlation. You can see that more or less all of the coordinates have absolute value greater than say 0.05. So it's not too bad. So we formalize this using this theorem, where I have written it for a random vector because we are interested in the first coordinate. So we say that the first coordinate after you apply this rotation will have some correlation which is a factor smaller than the original correlation, but this holds true with some probability, 1 by 28 here in this case. We prove this using this inequality. So what we have obtained is a constant probability of error guarantee for this one dimensional problem, where y and the x tilde is the rotated x, y and the first coordinate of the rotated vector have correlation which is greater than or equal to tau square by 2d, or is 0. So we can test between these two with constant probability of error guarantees. And what is the communication incurred here? You can recall this previous slide where we said if we can test for these scalars, and if it is known that rho square is greater than tau square, then the communication is of the order 1 by tau square. So here reciprocal of that. The communication here is d by tau square, but the guarantees are still not in terms of delta and epsilon like we had in the one dimensional case. Here we are saying if the rotation works, everything works, and the rotation we said work with some probability like 1 by 28 or something, some constant number, not like delta and epsilon. So how do we convert this constant probability of error guarantees to a general probability of error guarantees? We apply what is called a median trick. We construct several such tests, say little m of them, each of which have a constant probability of error guarantee, and we use all of their decisions and take the average of those decisions. So we can show this theorem which says that if you have a test which communicates L bits and has this alpha beta constant probability of error guarantees, then we can construct m such tests. So the communication is also m times L whenever this m is larger than certain quantity here. So L, as you can recall, and I have written here, is of the order d by tau square, and so ml is this bottom term times d by tau square. So the overall communication is given by d by tau square times this term. So this is the communication incurred by the scheme for this high dimensional correlation testing. But again, we have to ask the question, is this the best that we can do? So towards that, we would like to establish a lower bound. We go like before, and we show that using the hypercontractivity ideas, we can again show that the communication has to be at least d by tau square. So this matches this upper bound. So for one-way communication where party 1 sends something to party 2 and party 2 declares the output, in that case, our scheme is optimal. It is optimal in terms of dependence on d and tau square. But somehow if we allow interaction, meaning if we allow party 1 to send something to party P2, and party P2 upon observing these bits and again it sends something back and they communicate back and forth. If that is allowed, maybe there is some possibility of improving this. So what if we allow interactive communication instead of one-way communication? But we establish a lower bound which says that even when you allow interactive communication, you have to communicate an overall number of bits which is d by tau, order d by tau square. So whatever our one-way scheme achieves, that itself is optimal even when you allow interaction. So this settles the problem of this high dimensional correlation testing. But again, one question remains, which is that why can't you just estimate the vector rho and then calculate its norm? Here we did not estimate the vector rho, right? We reduced the problem to a one-dimensional problem and then solved it. So why can't we estimate the vector rho itself? But we establish another lower bound which says that in order to estimate the vector rho, you have to communicate d square over tau square, which is strictly larger than d by tau square. So estimating and testing doesn't work. So the conclusion is that whatever our scheme does is optimal, and obvious alternative schemes like estimating the vector do not provide the same guarantee. So overall, the result is that the communication complexity of this d-dimensional correlation testing that we defined here, where x is d-dimensional, y is a scalar, and we are asking if the energy of the correlation between y and the vector x, is it greater than tau square or is it 0? For this question, the communication complexity, rather the number of bits that you have to send, is of the order d by tau square. So with that, I end my presentation. I am open to questions or comments. Thanks.
If anyone has any questions, you may raise your hand and then you can ask the question. It seems that nobody has any questions. So thank you, Sahasranand, for this interesting talk. I hope it would have intrigued people working in even different areas. So thank you once again, Sahasranand, and will you please accept this memento as on behalf of IEEE-IISc ComSoc and SPS chapters. So we wish you all the best in your future endeavors.
Yeah, thank you, Arki, and I also want to thank the organizers for this opportunity, and thank you all for joining the talk.